All right, so this is Philipp Oppermann's blog. It's not something I wrote. This is something Philipp Oppermann wrote. And I'm just going through it step by step, entry by entry. And we are currently on paging implementation. This post shows how to implement paging support in our kernel. It first explores different techniques to make physical page table frames accessible to the kernel and discusses their respective advantages and drawbacks. It then implements an address translation function and a function to create a new mapping. All right. The previous post gave an introduction to the concept of paging. It motivated paging by comparing it with segmentation, explained how paging and page tables worked, and then introduced a 4-level page table design of the x86-64. We found out that the bootloader already set up a page table hierarchy for our kernel, which means that our kernel already runs on virtual addresses. This improved safety since illegal memory accesses cause page fault exceptions instead of modifying arbitrary physical memory. The post ended with the problem that we can't access the page tables from our kernel because they are stored in physical memory and our kernel already runs on virtual addresses. This post continues at this point and explores different approaches of making the page table frames accessible to our kernel. We will discuss the advantages and drawbacks of each approach and then decide for an approach for our kernel. To implement the approach, we will need support from the bootloader, so we'll configure it first. After, we will implement a function that traverses the page table hierarchy in order to translate virtual to physical addresses. Finally, we'll learn how to create new mappings in the page tables and how to find unused memory frames for creating new page tables. So basically, we're writing a full VM system. Accessing page tables from our kernel is not as easy as it may seem. To understand the problem, let's take a look at the example 4-level page table hierarchy of the previous post again. Right. This is what we looked at last time. The important thing here is that each table entry stores the physical address of the next table. This avoids the need to run a translation for these addresses too, which would be bad for performance and could easily cause endless translation loops. The problem for us is that we can't directly access physical addresses from our kernel since our kernel also runs on top of virtual addresses. For example, when we access address 4K, we access virtual address 4K, not the physical address 4K, where the level 4 page table is stored. When we want to access the physical address 4K, we can only do so through some virtual address that maps to it. So in order to access page table frames, we need to map some virtual address to them. There are different ways to create the mappings that allow us to access arbitrary page table frames. A simple solution is to identity map all page tables. In this example, we see various identity mapped page table frames. This way, the physical addresses of the page tables are also valid virtual addresses, so we can easily access the page tables at all levels starting from the CR3 register. However, it clutters the virtual address space and makes it more difficult to find contiguous memory regions of larger sizes. For example, imagine we want to create a virtual memory region of size 1000K in the above graphic. E.g., for example, for memory mapping a file. We can't start the region at 28K because it would collide with the already mapped page at 1004K. Oh, here. Okay. Right, each one of these is 4K. So we have to look further until we find a large enough unmapped area, for example, at 1008K. This is a similar fragmentation problem as with segmentation. Equally, it makes it much more difficult to create new page tables because we need to find physical frames whose corresponding pages aren't already in use. For example, let's assume that we reserve virtual 1000K memory regions starting at 1008K for our memory mapped file. Now we can't use any frame with a physical address between 1000K and 2008K anymore because we can't identity map it. Map at a fixed offset. To avoid the problem of cluttering the virtual address space, we can use a separate memory region for page table mappings. So instead of identity mapping the page table frames, we map them at a fixed offset in the virtual address space. For example, the offset could be 10 terabytes. By using virtual memory in the range 10 terabytes to 10 terabytes plus physical memory size exclusively for page table mappings, we avoid the collision problems of the identity mapping. Reserving such a large region of the virtual space is only possible if the virtual address space is much larger than physical memory size. This isn't a problem on x86-64, since the 48-bit address space is 256 terabytes large. This approach still has the disadvantage that we need to create a new mapping whenever we create a new page table. Also, it does not allow accessing page tables of other address spaces, which would be useful when creating new process. Yeah, and it also limits how many processes you can run, right? Because if each one gets to 256 terabytes, you have a limited number of those before you run out of address space. Map the complete physical memory. We can solve these problems by mapping the complete physical memory instead of only page table frames. This approach allows our kernel to access arbitrary physical memory, including page table frames, of other address spaces. The reserved virtual memory range has the same size as before, with the difference that it no longer contains unmapped pages. The disadvantage of this approach is that additional page tables are needed for storing mapping of the physical memory. These page tables need to be stored somewhere, so they use up a part of physical memory, which can be a problem on devices with a small amount of memory. On x86-64, however, we can use huge pages with the size of 2 megabytes for the mapping, instead of the default 4K pages. This way, mapping 32 gig of physical memory only requires 132K for page tables, since only one level 3 page table and 32 level 2 tables are needed. Huge pages are also more cache efficient since they use fewer entries in the translation look-aside buffer. Temporary mapping. For devices with very small amounts of physical memory, we could map the page table frames only temporarily when we need to access them. To be able to create the temporary mappings, we only need a single identity mapped level 1 table. Not sure I follow. The level 1 table in this graphic controls the first 2 meg of the virtual address space. This is because it's reachable by starting at the CR3 register and following the 0th register entry in level 4, level 3, and level 2. The entry with index 8 maps the virtual page at address 32K to the physical frame at address 32K, thereby identity mapping the level 1 table itself. The graphic shows this identity mapping by the horizontal arrow. Here. Okay. By writing to the identity map level 1 table, our kernel can create up to 511 temporary mappings. In the above example, the kernel created 2 memory mappings. 0th entry of level 1 created a temporary mapping of virtual page 0, physical frame of level 2 page. Okay. And the 9th entry of level 1 with address 4K created a temporary mapping of virtual page 36 to the physical frame of level 4 page. Okay. Now the kernel can access level 2 page table by writing page 0K and level 4 page table by writing to page 36K. That's complicated, right? The process for accessing an arbitrary page table frame with temporary mappings would be search for a free entry in the identity mapped level 1 table, map that to a physical frame of the page table we want to access the target frame through the virtual page that maps to the entry, and then set the entry back to the set the entry back to unused, thereby removing the temporary mapping again. Then we have recursive page tables. Another interesting approach that requires no additional page tables at all is to map the page table recursively. The idea behind this approach is to map some entry of the level 4 page table to the level 4 page itself. By doing this, we effectively reserve a part of the virtual address space and map all current and future page table frames to that space. But the level 4 page points to more than just one frame, right? The only difference to the example at the beginning of this post is the additional entry at 511 in the level 4 page table, which is mapped to physical frame 4K, the frame of the level 4 page table itself. So it just maps itself to itself. Okay. By letting the CPU follow this entry on translation, it doesn't reach a level 3 table, but the same level 4 table again. This is similar to a recursive function that calls itself. Therefore, this table is called a recursive page table. The important thing is that the CPU assumes that every entry in the level 4 page table points to a level 3. So now it treats level 4 as level 3. This works because the table of all levels have the exact same layout. By following a recursive entry one or multiple times before we start the actual translation, we can effectively shorten the number of levels that the CPU traverses. For example, if we follow the recursive entry once and then proceed to the level 3 table, the CPU thinks that level 3 is level 2. Going further, it treats level 2 as level 1. Level 1 is as the table mapped in the mapped frame. This means we can now read and write the level 1 page table because the CPU thinks that it is the mapped frame. The graphic below illustrates the 5 translation steps. Okay. I think I understand it, but I wouldn't be able to explain it, so I don't understand it fully, I guess. We can follow the recursive entry twice before starting the translation to reduce the number of traverse levels to 2. Is this what we're going to implement? Because I don't want to read all of this if we're not going to do it. Recursive paging is an interesting technique that shows how powerful a single mapping in a page table can be. It's relatively easy to implement and only requires a minimal amount of setup. So it's a good choice for first experiments with paging. However, it also has some disadvantages. It occupies a large amount of virtual memory, 512 gigabytes. This isn't a big problem in the large 48-bit address space, but it might lead to suboptimal cache behavior. It only allows accessing the currently active address space easily. Accessing other address spaces is still possible by changing the recursive entry, but a temporary mapping is required for switching back. We described how to do this in the outdated Remap the Kernel post. It heavily relies on the page table format of x86 and might not work on other architectures. All right. I'm just reading this over here. So this is just mapping the level 4 to level 3, but it's reading the same page again. And then reads from level 3 to level 2, but it's still on the level 4 table. Okay. All right. So bootloader support. All of these approaches require page table modifications for their setup. For example, mappings for the physical memory need to be created, or an entry of the level 4 needs to be mapped recursively. The problem is we can't create these required mappings without an existing way to access page tables. This means we need the help of the bootloader, which creates the page tables that our kernel runs on. The bootloader has access to the page tables, so it can create any mappings that we need. In its current implementation, the bootloader crate has support for 2 of the above approaches, controlled through the cargo features. The map physical memory feature maps the complete physical memory somewhere in the virtual address space. Thus, the kernel can access all physical memory and can follow the map complete physical memory approach. With the recursive page table feature, the bootloader maps an entry of the level 4 table recursively. This allows the kernel to access the page tables as described in the recursive page table section. We choose the first approach for our kernel since it's simple, platform independent, and more powerful. It also allows access to non-page table frames. To enable the required bootloader support, we add map physical memory feature to our bootloader dependency. Okay, so we have bootloader. We're using 9.22. They've got 9.8, but the features should still work, right? Features equals map physical memory. With this feature enabled, the bootloader maps the complete physical memory to some unused virtual address space. To communicate the virtual address range to our kernel, the bootloader passes the boot information structure. The bootloader crate defines a boot info struct that contains all the information it passes to our kernel. The struct is still in an early stage, so expect some breakage when updating future semver incompatible bootloader implementations. What's a semver incompatible? Oh, That's not a link to Semper incompatible bootloader implementations. That's a link to the crate thing that says how to select versions of crates. Okay. With the map physical memory feature enabled, it currently has two fields, memory map and physical memory offset. The memory map field contains an overview of the available physical memory. This tells our kernel how much physical memory is available in the system and which memory regions are reserved for devices such as VGA hardware. The memory map can be queried from the BIOS or UEFI firmware, but only very early in the boot process. For this reason, it must be provided by the bootloader because there is no way for the kernel to retrieve it later. We will need that memory map later in this post. The physical memory offset tells us the virtual start address of the physical memory mapping. By adding this offset to the physical address, we get the corresponding virtual address. Okay, that makes sense. This allows us to access arbitrary physical memory from our kernel. The bootloader passes the boot info struct to our kernel in the form of a static boot info argument to our start function. Okay. Well, let's save this first. Okay. So in our start function, we now have boot info, which is a static. Okay. It wasn't a problem to leave off this argument before because the x86-64 calling convention passes the first argument, like the first four arguments, right, in the CPU register. Thus, the argument is simply ignored when it isn't declared. However, it would be a problem if we accidentally use the wrong argument type, since the compiler doesn't know the correct type signature of our entry point function. So, the entry point macro. Since our start function is called externally from the bootloader, no checking of our function signature occurs. This means we could let it take arbitrary arguments without any compilation errors. That's a shame. What is this? It's unknown. Oh, do we have to import boot? Oh, we do. I missed that. Use bootloader boot info entry point. Okay, so now this should be boot info, right? Yep. To make sure that the entry point function has always the correct signature that the bootloader expects, these two words are flipped around. The bootloader crate provides an entry point macro that provides a type-checked way to define a Rust function as the entry point. Let's rewrite our entry point function to use this macro. Okay. So we have this entry point. And then we have, oh, we get rid of no mangle. And we just say kernel main. Okay. We no longer need to use the extern C or no mangle for our entry point, as the macro defines the real lower-level start entry point for us. The kernel main function is now a completely normal Rust function, so we can choose an arbitrary name for it. The important thing is it is type-checked, so that a compilation error occurs when we use a wrong function signature, for example, by adding an argument or changing the argument type. So if I build this and spell the macro correctly, we still have two warnings. Oh, because we're not using boot info. Okay, that makes sense. If I specify the wrong argument, it should fail now, right? Yeah, expected bootloader boot info. Okay. Good. Let's perform the same change in our lib.rs. So we get rid of that. We get rid of those. We change this to test kernel main. And we're going to add entry point. Oh, test kernel main. All right, and then up here, use bootloader and boot info. And I think this is going to fail to compile because I didn't add the argument, right? Ooh. Oh, because it's, right, if I tried to test, it should fail to build. Yeah. Okay, because we're missing the boot info. Right? So now the test should succeed. Yep. All the tests are passing. Good. Since the entry point is only used in test code, we add the config test attribute to all the items. Oh, did I forget that one up here? No, I didn't. I remembered it. Good. We give our test entry point a distinct name, test kernel main, to avoid confusion with the kernel main of our main RS. We don't use the boot info parameter for now, so we prefix the parameter name with an underscore to silence the unused variable warning. Now that we have access to physical memory, we can finally start to implement our page table code. First, we will take a look at the currently active page tables that our kernel runs on. In the second step, we will create a translation function that returns a physical address that a given virtual address is mapped to. As the last step, we will try to modify page tables in order to create a new mapping. Before we begin, we create a new memory module for our code. Oh, in main, we're going to add, in lib. Pub mod memory. And it doesn't exist, so let's create it. At the end of the previous post, we tried to take a look at the page table our kernel runs on, but failed since we couldn't access the physical frame that the CR3 register points to. We are now able to continue from there by creating an active level 4 table function that returns a reference to the active level 4 page table. Okay. We have structures, paging, page table, and we also have vert adder. I'm not going to add the comment. Ooh, it's an unsafe function. Active level 4 table. It returns a static mute page table. Okay, so use x86. Oh, this is what we had before, right? In main. Oh, okay. Let phys is equal to level 4 table frame start address. Vert is the physical memory offset plus the phys as U64. And then let page table pointer is a mute page table vert as mute pointer. And that's why it has to be unsafe, right? And we're returning a page table pointer. Exciting. Now we're just pointing into memory somewhere, and we're just hoping our calculation is correct. All right, let's see if this builds. It does not. Oh. Okay. First, we read the physical frame of the active level 4 table from the CR3 register. We then take its physical start address, convert it to a U64, and add it to the physical memory offset to get the virtual address where the page table frame is mapped. Finally, we would convert the virtual address to a star mute page table raw pointer through the asMutePointer method, and then unsafely create a mute page table reference from it. We create a mute reference instead of a non-mutable, immutable reference because we will mutate the page tables later in this post. We don't need to use an unsafe block here because Rust treats the complete body of an unsafe function like a large unsafe block. This makes our code more dangerous, since we could accidentally introduce an unsafe operation in previous lines without noticing. It also makes it much more difficult to spot the unsafe operations. There is an RFC to change this behavior. We can now use this function to print the entries of the level 4 page table. Okay. So in here, oh, in main. Here we go. So we're going to say use BlogOS memory level 4 table. Oh, GRM says typo in entry point a while ago. Sorry for missing that. Yeah, generally typo, the compiler is going to catch typos for me, so vert adder. Okay, so we still have our hello world, we still have our init, and now we're going to pull this out, and we're going to say let phys mem offset equals vert adder new boot info memory offset for table is equal to unsafe active level 4 table phys mem offset. And now we're going to print them all out. For I, an entry in L4 table header enumerate. Okay. Println L4 entry I is equal to entry. Right? So this just print out each entry, and I don't know if this is going to decode the entries for us or just print out the bits. I guess we can see it here. All right. So we're able to get the physical memory offset from the boot info. Boot info comes in here. We translate it to a virtual address type. We then pass that into the active level 4 table, which looks up the actual location of the level 4 table and returns the whole table unsafely. And then we can read the entries from that table when we print them out. Okay, let's run that. We got the same, very similar here. We have entry 0, 2, 3, and 31. And each one of those is mapped to a different physical address. Present, writable, and accessed. And these are dirty. So we're writing to these guys, but we haven't written to this guy. I guess there isn't... So they were talking before about the VGA at OX B8000. And that's not part of this table here, so... We see there are various non-empty entries which all map to different level 3 tables. There are so many regions because kernel code, kernel stack, and physical memory mapping and boot information all use separate memory areas. To traverse page tables further and take a look at the level 3 table, we can take the mapped frame of an entry and convert it to a virtual address again. Okay. So we have to go through the whole process, right? This is the, memory accesses are slow if you don't have a cache kind of thing. So we're going to add this here. We're going to add structures, paging, page table. Okay. And then if it's not used, we have a level 4 entry, and then we can do this. Let phys and equal entry frame unwrap start address. Vert is equal to phys as U64 plus boot info physical memory offset. Our pointer is equal to a new virtual address And then the level 3 table is equal to, I guess we have to tell it it's a page table, unsafe pointer. And then we can print those entries. Entry, like that. So now we have all the level 3s, and those should all get dumped out. And there should be a lot more of those, right? There we go. So if we run this, we got a whole bunch. Oop, and I typoed the entry. I have a capital Y on entry. But now we're seeing a lot more. And of course, it's scrolling off the screen because we've lost the location. We're not dumping it out to a scrollable window. But we can see there's each level 4 has a bunch of level 3s. So that's kind of neat. If we're looking at level 2 and level 1 tables, we repeat that process. As you can imagine, this gets very verbose quickly, so we don't show the full code here. Yeah, I'm not going to do it either. Traversing page tables manually is interesting because it helps to understand how the CPU performs a translation. However, most of the time we're only interested in the mapped physical address for a given virtual address. So let's create a function for that. For translating a virtual address to a physical address, we have to traverse the 4-level page table until we reach the mapped frame. Let's create a function that performs this translation. So, okay, let's actually showing level 4 and level 3 page tables. Right? So in memory, I'm going to add phys_adder here, and we have another function and it returns an option of phys_adder. Translate adder inner. Okay. I'm sure there's going to be a reason for this extra layer of indirection here. We forward the function to a safe translate adder inner function to limit the scope of unsafe. As we noted above, Rust treats the complete body of an unsafe function like a large unsafe block. By calling into a private safe function, we make each unsafe operation explicit again. Okay. All right. The private inner function contains the real implementation. It's going to be the same thing here, right? Except without the unsafe. So use x86, 64, I mix the x there, structures, paging, page table, frame error, and then registers, control, CR3. Okay? We got the same line here. And then let table indexes this is interesting. Adder P2 index and adder P1 index. This must be pulling out those bits from the address. Right? Remember the address has 12 bits at the bottom for the index into the frame, and then 4 different 9-bit components. So let root frame is equal to level 4 table frame. So we start with the frame from level 4, and then we're going to traverse each one. convert the frame into a page table reference. Vert is physical memory offset plus frame start address as U64. So that's a safe operation. Let table pointer is a constant pointer to a page table This is safe. Interesting. So we can just grab a pointer into memory and we call it safe. Let table, this is unsafe. Table pointer. Okay. Then we're going to read the page table entry and update the frame. I don't know why there are backticks there, but okay. Let entry is table index. Frame is equal to match entry frame. Right, so we're updating this frame value. We used it here, and now we're updating it here because we're updating it in the loop. Because the next time through the loop, we're going to reuse that frame. That makes sense. It might return none. Okay. Panic. Huge frame, huge pages not supported. And then that's that. And then we're going to return some frame.start address plus U64 from header page offset. So after we've looped through each one of the indices, page 4 index, page 3, page 2, page 1, we're updating frame each time through the loop. Epic Blog says, yeah, only dereferencing raw pointers is unsafe. Yeah, that makes sense. So creating the pointer is fine. It's when we dereference it that it's unsafe. Okay, instead of reusing our active level 4 table function, we read the level 4 frame from the CR3 register again. We do this because it simplifies this prototype implementation. Don't worry, we'll create a better solution in a moment. Okay. Panic is a macro. Translate adder. Oh, okay. Yep. What else? Start address. There we go. The vert adder struct already provides methods to compute the indexes into the page tables of the 4 levels. Yeah, that's what we see here. We store these indexes in a small array because it allows us to traverse the page tables using a for loop. Outside of the loop, we remember the last visited. So it would be nice if adder had like an iter, right? An index iter on it. What does adder look like? It's just a vert adder. Oh. Yeah, but where's the impl for it? Here it is. Can create a new one. New unsafe 0. There's the as U64. I wonder why they didn't write a from instead of creating okay. Well, getting in the weeds. But this would be neat, like if they created an adder iterator for the indexes, right? We could just say for index in adder.iter indices, right? And then do this logic, right? Instead of splitting it out like that. Maybe I'll submit a PR. All right. Outside the loop, we remember the last visited frame to calculate the physical address later. The frame points to page table frames while iterating and to the map frame after the last iteration. Inside the loop, we again use the physical memory offset to convert the frame into a page table reference. We then read the entry of the current page table and use the page table entry frame function to retrieve the mapped frame. If the entry is not mapped to a frame, we return none. If the entry maps to a huge 2 meg or 1 gig page, we panic for now. Let's test our translation function by translating some addresses. Okay, let's do that. This build, right? We'll go back to main. We're going to pull this code out. And we're going to use translate adder. We still need to grab the physical memory offset. We don't need any of this though. What we do need is we're going to create an array of addresses to look up. That's the VGA table, right? 201.008. That's a code page. We have a stack page. This one might not work because the stack looks very different. And then we have our boot address, our physical memory address, boot info, physical memory offset. That should fit on one line, yep. For address in addresses. Do we need this ampersand here? I didn't think so. Okay, so we're going to translate each one and then print it out. So it's just vert translates to phys. And it blew up because I forgot something. Oh, I need an equal sign, obviously. We're still not using this boot info, right? Oh, we are. We're using it right there. Oh, we're not using the page table anymore. We are using bird adder though. Okay. Okay. Cargo run. All right. When we run it, we see the following output. Vert adder B8000 is to physical address B8000. Vert adder this is to phys adder. Okay, that map's the same. And this stack address, I guess somehow it worked, it maps to this other address here. Panicked that huge page is not supported. Okay, so this is happening because I guess the bootloader physical address is a huge page table. As expected, the identity mapped address B8000 translates to the same physical address. The code page and stack page translate to some arbitrary physical addresses which depend on how the bootloader created the initial mapping for our kernel. It's worth noting that the last 12 bits always stay the same after translation. Yeah, these the last 12 bits are the last 3 hex digits. So we see 000, 000, 08, 008, A10 is A10. Which makes sense because these bits are the page offset and not part of the translation. Since each physical address can be accessed by adding the physical memory offset, the translation of the physical memory offset address itself should point to physical address 0. However, the translation fails because the mapping uses huge pages for efficiency, which is not supported in our implementation yet. Using offset page table. Translating virtual to physical addresses is a common task in an OS kernel, therefore the x86-64 crate provides an abstraction for it. The implementation already supports huge pages and several other page table functions apart from translate adder, so we will use it in the following instead of adding huge page support to our own implementation. The base of the abstraction are the 2 traits that define various page table mapping functions. The mapper trait is generic over the page size and provides the functions that operate on pages. Example are translate page, which translates a given page to a frame of the same size, and map to, which creates a new mapping in the page table. The translate trait provides functions that will work with multiple page sizes, such as translate adder or the general translate. The translate only define The traits only define the interface. They don't provide any implementation. The x86-64 crate currently provides 3 types that implement the traits with different requirements. The offset page table type assumes that the complete physical memory is mapped to the virtual address space at some offset. The mapped page table is a bit more flexible. It only requires that each page table frame is mapped to the virtual address space at a calculable address. Finally, the recursive page table type can be used to access page table frames from recursive page tables. In our case, the bootloader maps complete physical memory at a virtual address specified by the physical memory offset variable. So we can use the offset page table type. To initialize it, we create a new init function for our memory module. Translating phys vert to phys. Example. Oh. There. Okay, so in memory, there we go. We're going to add to paging, we have page table and offset page table. Okay. And now we're going to have an init function. Let's put that at the top. And it returns an offset page table static. Let level 4 table active level 4 table. Wow, I keep doing that. And we're going to return offset page table new level 4 table offset. Done. And then we're going to make this guy private. Okay. This function takes the physical memory offset as an argument and returns a new offset page table instance with static lifetime. This means that the instance stays valid for the complete runtime of our kernel. In the function body, we first call the active level 4 page table function to retrieve a mutable reference to the level 4 page table. When we invoke page table offset page table new function with this reference, we then invoke. As the second parameter, the new function expects the virtual address at which the mapping of the physical memory starts, which is given in the physical memory offset variable. The active level 4 table function should only be called from the init function from now on, because it can easily lead to aliased mutable references, which, when called multiple times, which can cause undefined behavior. For this reason, we make the function private by removing the pub specifier. We can now use the translate adder method instead of our own memory translate adder function. We only need to change a few lines in our kernel main. So we wrote all that code, and now we're throwing it away. So instead of translate adder, we're going to call translate adder. We still have this. And we just need to add structures. Paging, translate, like that. And then we're going to set up the mapper. Let mapper unsafe. Oh, this goes here, like that. Then we have the addresses. We do vert adder new, and then here we have mapper translate adder. Okay, so this is calling our memory init. So it's outside of this BlogOS init. I wonder if that's something we need to refactor. Let's see, does this build? It does not. Oh, because it only takes one argument. Okay, and then our translate adder no longer is needed. So we blow away all this code. Now we have 4 warnings. Okay, let's clean those up. We don't need phys_adder anymore. And then, oh, this is no longer unsafe. Okay. Yeah, okay, there we go. We need to import the translate trait in order to use the translate adder method it provides. When we run it now, we see the same translation results as before. Except now it didn't panic on the last one. Okay. Hedgin, thank you for the raid. I'm actually almost wrapping up too. So, how was your stream? I got the notification and it said no rust, so I wasn't sure what you were doing. Good luck on your interview. Take care. As expected, the translations of B8000 and the code stack addresses stay the same. Additionally, we now see that the virtual address physical memory offset is mapped to physical address 0. By using the translation function of the mapped page table type, we can spare ourselves the work of implementing a huge page table support. We also have access to other page functions such as map_to, which we will use in the next section. At this point, we no longer need our memory translate adder and memory translate adder inner functions, so we can delete them. Okay, so until now, we only looked at page tables without modifying anything. Let's change that by creating a new mapping for a previously unmapped page. Okay, so now we're going to get exciting. Let's commit these changes. Use the crate provided memory translation. There we go. Until now, we only looked at page tables without modifying anything. Right? Oh, I just read that. We will use the map_to function of the mapper trait for our implementation. So let's take a look at that function first. The documentation tells us that it takes 4 arguments: the page that we want to map, the frame that the page should be mapped to, a set of flags for the page table entry, and a frame allocator. The frame allocator is needed because mapping the given page might require creating additional page tables, which need unused frames as backing storage. A create example mapping function. The first step of our implementation is to create a new create example mapping function that maps a given virtual page to B8000. Okay, we already have that. But okay, the physical frame of the VGA text buffer. We choose that frame because it allows us to easily test if the mapping was created correctly. We just need to write to the newly mapped page and see whether we see the right appear on the screen. So this is what the create mapping function looks like. All right. Oh, now we have to put phys_adder back. And in paging, we have to add page is frame mapper size 4KIB and frame allocator. That's going to spread everything out. That's fine. All right, and then pub fun create example mapping. Takes a page, a mapper, and a frame allocator. Yeah. Let's fix that. There we go. Okay. And then we're going to do another use. Okay. I'm not a huge fan of these uses in the middle, but maybe that's because I'm an old fogey. And let frame is equal to phys frame containing address phys_adder new B8000. So this is interesting. So we're using these So I wonder how this all works, or is this just creating a, oh, this is still unknown. It should know at some point that that we have a size like that. We'll find out. Flags is equal to flags present and flags writable. Unsafe. Fix me. This is not safe. We only do it for testing. Mapper map to page frame flags and frame allocator. Map to result expect. Map to failed. Flush. I wonder what's flushing. Okay. In addition to the page that should be mapped, the function expects a mutable reference to an offset page table instance and a frame allocator. The frame allocator parameter uses the impl trait syntax to be generic over all types that implement the frame allocator trait. The trait is generic over page size trait to work with both standard 4K pages and huge 2 meg 1 gig pages. Epic Blog is agreeing with me, so I'm going to highlight that one. Same here. I want to collect all the uses at the top. I did find there's a reason to learn to stick uses into function bodies when developing proc macros, though. Okay, that makes sense. I've never done proc macros, but that would be... I understand why you'd want to wrap them up in there. We only want to create 4K mapping, so we set the generic parameter to size 4K. The map2 method is unsafe because the caller must ensure that the frame is not already in use. Okay, the reason for this is that mapping the same frame twice could result in undefined behavior. For example, when two different mute references point to the same physical memory location. In our case, we reuse the VGA text buffer frame, which is already mapped, so we break the required condition. However, the create example mapping function is only temporary testing function and will be removed after this post, so it is okay. To remind us of the unsafety, we put a fix me comment in the line. I'll just say that. In addition to page and unused frame, the map2 method takes a set of flags for the mapping and a reference to the frame allocator, which will be explained in a moment. For the flags, we set the present flag because it's required for all valid entries, and the writable flag to make the mapped page writable. For a list of all possible flags, see the page table format. Okay. The map2 function can fail, so it returns a result. Since this is just some example code that does not need to be robust, we just use expect to panic when an error occurs. On success, the function returns a mapper flush type that provides an easy way to flush the newly mapped page from the translation look-aside buffer with its flush method. Oh, okay, so that's what we're flushing. We're flushing the result. Oops. The mapper flush. So, okay, now it knows it's size 4K. All right. And it calls flush on mapper flush. All right. Like result, the type uses the must use attribute to emit a warning when we accidentally forget to use it. Huh. Can we see that? Is that anywhere? I'm just going to see if I can jump to it. Oh, it doesn't know that. It knows it here. Oh, I probably have to import it, right? Nope. Okay. I wanted to take a look at it, but I guess that'll have to wait. A dummy frame allocator. To be able to call create example mapping, we need to create a type that implements frame allocator trait first. As noted above, the trait is responsible for allocating frames for new page table if they are needed by map2. Let's start with a simple case and assume that we don't need to create new page table entries. For this case, the frame allocator that always returns none suffices. We create such an empty frame allocator for testing our mapping function. Okay. Implementing the frame allocator is unsafe because the implementer must guarantee that the allocator yields only unused frames. Otherwise, undefined behavior might occur. For example, when two virtual pages are mapped to the same. Okay. Our empty frame allocator only returns none, so this isn't a problem in this case. We now have a simple frame allocator that we can pass to our create example mapping function. However, the allocator always returns none, so this will only work if no additional page table frames are needed for creating the mapping. To understand when additional page table frames are needed and when not, let's consider an example. The graphic shows a virtual address space on the left, physical address space on the right, and the page tables in between. The page tables are stored in physical memory frames, indicated by the dashed lines. The virtual address space contains a single mapped page at address this, marked in blue. To translate this page to its frame, the CPU walks the 4-level page table until it reaches the frame at address 36K. Additionally, the graphic shows the physical frame of the VGA text in red. Our goal is to map a previously unmapped virtual page to this frame using our create example mapping function. Since our empty frame allocator always returns none, we want to create the mapping so that no additional frames are needed from the allocator. This depends on the virtual page that we select for the mapping. The graphic shows two candidate pages in the virtual address space, both marked in yellow. One page is at address this, which is 3 pages before the mapped page in blue. Okay. While the level 4 and level 3 page table indices are the same as for the blue page, the level 2 and level 1 indices are different. The different index of the level 2 table means that a different level 1 table is used for this page. Since this level 1 table does not yet exist, we would need to create it if we chose that page for example mapping, which would require an additional unused physical frame. In contrast, the second candidate page, this one here, does not have this problem because it uses the same level 1 page table as the blue page. Thus, all required page tables already exist. In summary, the difficulty of creating new mapping depends on the virtual page that we want to map. In the easiest case, level 1 page table for the page already exists and we just need to write a single entry. In the most difficult case, the page is in a memory region for that no level 3 exists yet. So we need to create a new level 3, level 2, and level 1 pages tables first. For our create example mapping function with the empty frame allocator, we need to choose a page for that all page tables already exist. I'm getting lost in the English here. To find such a page, we can utilize the fact that the bootloader loads itself in the first megabyte of the virtual address space. This means that a valid level 1 table exists for all pages in this region. Thus, we can choose any unused page in this memory region for our example mapping, such as the page at address 0. Normally, this page should stay unused to guarantee that dereferencing a null pointer causes a page fault, so we know that the bootloader leaves it unmapped. That's tricky. Okay, we now have all the required parameters for calling our create example mapping function, so let's modify our kernel main. To map the page at address 0. Since we map the page to be the frame of the VGA text buffer, we should be able to write to the screen through it afterwards. All right, so I guess we're getting rid of these guys here. We still have the mapper, but now we're going to say let frame allocator at some point we're going to have an actual frame allocator, right? So we're just picking 0 because we know that's mapped. Okay, and then we're going to write to it. Let page pointer is equal to this page start address as mute. Oops. F021. What the heck? F077, F065, F04E. Oh, I see what they're doing. Right, so they're basically writing 4 characters. 21 is exclamation point. I forget what the ASCII 65 is A, right? And 4E. I don't know what that says. But we'll find out in a second because it's going to write directly to offset 400 in we no longer need translate, right? So we just change it to page. Oops. Oh, this has to be mutable mapper now. Okay. So let's see what we're writing. Oh, that's right. It's backwards. New, bang. Yeah. And the F0 is right, is a black text on white background. And I was thinking it was forward, but it's not. It's backwards. So it must be N, E. Oh, that's E, not A. E, that's the W, and that's the exclamation mark. Okay. We first create the mapping for the page address 0 by calling a create example mapping function with a mutable reference to the mapper and the frame allocator instances. This maps the page to VGA text buffer frame, so we should see any write to it on the screen. Then we convert the page to a raw pointer and write the value to offset 400. We don't write to the start of the page because the top line of the VGA buffer is directly shifted off the screen by the next println. We write the value this, which represents the string new exclamation mark on the white background. As we learned in the VGA text mode post, writes to VGA buffer should be volatile, so we use the write volatile method. And there it is. The new on the screen is by our write to page 0, which means that we successfully created a new mapping in the page tables. Creating that mapping only worked because the level 1 table responsible for the page at address 0 already exists. When we try to map a page for I think this should be for which. When we try to map a page for which no level 1 table exists yet, the map to function fails because it tries to allocate frames to from the empty frame allocator for creating new page tables. We can see that happen when we try to map page this instead of 0. When we run it, a panic with the following error message occurs. So if we don't do 0, instead we do the dead beef thing here. And we should get the panic. Panic map to failed. Frame allocation failed. Right? 9995. Wow. Here we're getting a memory address. That's interesting. That the old version used to map to the result. The new one maps to here. The actual line that panics. Okay. To map pages that don't have a level 1 page table yet, we need to create a proper frame allocator. But how do we know which frames are unused and how much physical memory is available? In order to create new page tables, we need to create a proper frame allocator. For that, we use the memory map that is passed by the bootloader as part of the boot info struct. Okay. So now we're going to say use bootloader boot info memory map. A frame allocator that returns usable frames from the bootloader's memory map. Okay, so we're creating this new thing here. Nope, it's not that. It's CMT. Oh, I forgot how to expand it now. Okay. Nope, come on. There we go. And this is a boot info allocator. Okay, so we have pub struct boot info frame allocator. Next is usize, and then we're going to implement it. Wow, I just can't type the word memory. Okay, the struct has two fields, a static reference to the memory map passed by the bootloader and a next field that keeps track of a number of next frame that the allocator should return. As we explained in the boot information section, the memory map is provided by the BIOS UEFI firmware. It can only be queried very early in the boot process, so the bootloader already calls the respective functions for us. The memory map consists of a list of memory region structs which contain the start address, the length, and the type of each memory region. The init function initializes a boot info frame allocator with a given memory map. The next field is initialized with 0 and will be increased for every frame allocation to avoid returning the same frame twice. Since we don't know if the usable frames of the memory map were already used somewhere else, our init function must be unsafe to require additional guarantees from the caller. A usable frames method. Before we implement the frame allocator trait, we add an auxiliary method that converts the memory map into an iterator of usable frames. Okay. So we're going to create this brand new iterator from a map call. We're getting this iterator though, right? From the regions. Let usable regions, regions filter our region type, memory region type usable. Okay. And then each address range we map okay, so this is just creating the map. It's actually not creating the ranges yet. And then let frame addresses flat map step by 4096. Huh. Okay. And then we're going to return frame addresses.map. Adder. new adder, like that. Okay, so that returns a map. Oh, Chinapati, thank you for the follow. Much appreciated. Yeah, frame addresses.map adder phys. Okay, so this is just returning a map, which implements iterator on physframe. Okay. This function uses iterator combinator methods to transform the initial memory map into an iterator of usable physical frames. First, we call the iter method to convert the memory map into an iterator of memory regions. We use the filter to filter out the usable ones. Sorry, to filter out the unusable ones and keep the usable ones. Then we use map to create ranges. Right? So these are actually just ranges. This is a map. Right? It says unknown. That's an iter of memory region. That results in the filter. This is an unknown. Oh, I need to include a memory region type somewhere. Maybe that's why it was unknown. No, it's still unknown. That's why it's unknown. There we go. Yeah, so now it's a map of a filter of an iterator. Okay. Afterwards, we use the map combinator and Rust's range syntax to transform our iterator of memory regions into an iterator of address ranges. And we use flat map to transform the address ranges into an iterator of frame start addresses, choosing every 4096th address using step by. So that's 4K. Finally, we convert the start addresses to physframe types to construct an iterator. The return type of the function uses the impl trait feature. This way we can specify that we return some type that implements the iterator. I guess I should get this to build first, instead of having it sit there doing nothing. Okay. We don't need to rename the concrete return type. Yeah, we just say it implements this. So as long as we return something that implements this, Rust will map it. This is important here because we can't name the concrete type since it depends on unnamable closure types. Now we can implement the frame allocator trait, which is this thing here. That's interesting. We're using the nth. I guess because we're not storing the frame iterator anywhere in here, we have to grab all the usable frames each time. We use O of n to find the one we're looking for, and then we... That's too bad. That we couldn't just peel it off, or store the iterator here and peel each one off each time. We first use the usable frames method to get an iterator of usable frames from the memory map. Then we use the iterator nth function to get the frame with that index. Before returning the frame, we increase self next, so that we return the following frame on the next call. This implementation is not quite optimal since it recreates the usable frame allocator in every allocation. It would be better to directly store the iterator as a struct field instead. Then we wouldn't need the nth method and can just call the next function. But this doesn't work. Oh, do I need to do something else? Oh, yes I do. I have to call this boot info frame allocator. And that goes away. And then this has to change, right? I'm sure we're going to get there. Oh, and we have to pass it in. boot info memory map. Like that. There we go. Okay. With the boot info frame allocator, the mapping succeeds and we see the black on white news on the screen again. Really? Why would we see that? Because this shouldn't map. Or maybe that was temporary. Maybe we want to change this to B8000. Oops. Well, let's see. Let's see. Let me run this. Because I think I'm missing something. Why would the new show up on the screen? It does. Okay. And I must be missing something. B8000. Oh, okay, because we're always mapping it to the physical address B8000 no matter what the virtual memory address is. Okay. That makes sense. Okay, so we can now modify our kernel main, right? We did that. And then new shows up on the screen again. Behind the scenes, the map2 method creates the missing page tables in the following way. Allocate an unused frame from the past frame allocator, zero the frame to create a new empty page table, map the entry of a higher level table to that frame, and continue with the next table level. So that happens all behind the scenes for us. While a create example mapping function is just some example code, we are now able to create new mappings for arbitrary pages. This will be essential for allocating memory or implementing multi-threading in future posts. At this point, we should delete the create example mapping function again to avoid accidentally invoking undefined behavior as explained above. Okay, so let's blow this away. Let's blow that away. Let's move this down here because this is really implementing the boot thing here. Let's go back to main and we're going to delete this code because we can't use it. And I guess this gets underscored then. Oh, we're not using mapper yet, so I just want to clean this up before pushing it. So in memory, we don't need mapper. We don't need page. And then in main, back in main, we don't need page either. Okay. And that's going to wrap this whole thing up. We did add, we got rid of all that stuff. And now we added a usable frame allocator, boot info frame allocator. Boot info frame allocator. Basic implementation. Obviously, it's going to have to get better. We don't want to grab usable frames every time we need a new frame, unused frame. And then we need to be able to free frames, and we don't have that either. So this is just the allocator side of things. All right, let's get that up and wrap things up. All right, the next stream will be heap allocation.